really complicated models, and at the low level you can put in your own APIs, you can move that stuff around. And most recently we have the TF code can run on multiple platforms. And so you have your CPU, which is basically like on the computer I'm running on, I have 8 cores and 16 dedicated threads. I hear they now have one out there that has over 100 cores. So you have your CPU running, and then you have your GPU, which is your graphics card. And most recently they also include the TPU setup, which is specifically for TensorFlow models, neural network kind of setup. So now you can export the TF code and it can run on all kinds of different platforms for the most diverse setup out there. And moving on from the hierarchy to the architecture, in the TensorFlow 2.0 architecture, we have, you can see on the left, this is usually where you start out with, and 80% of your time in data science is spent pre-processing data, making sure it's loaded correctly and everything looks right. So the first level in TensorFlow is going to be your read and pre-processed data, your TF data feature columns. This is going to feed into your TF Keras or your pre-made estimators, and kind of you have your TensorFlow hub that sits on top of there so you can see what's going on. Once you have all that set up, you have your distribution strategy. Where are you going to run it? Are you going to be running it on just your regular CPU? Are you going to be running it with the GPU added in? Like I have a pretty high-end graphics card, so it actually grabs that GPU processor and uses it. Or do you have a specialized TPU set up in there that you paid extra money for? It could be if you're later on, when you're distributing the package, you might need to run this on some really high processors because you're processing it at a server level for, let's say, you might be processing this at you're distributing it, not the distribution strategy, but you're distributing it into a server where that server might be analyzing thousands and thousands of purchases done every minute. And so you need that higher speed to give them a recommendation or a suggestion so they can buy more stuff off your website. Or maybe you're looking for data fraud analysis working with the banks. You want to be able to run this at a high speed so that when you have hundreds of people sending their transactions in, it says, hey, this doesn't look right. Someone's scamming this person and probably has their credit card. So when we're talking about all those fun things, we're talking about saved model. We were talking about that earlier, where it used to be when you did one of these models, it wouldn't truncate the float numbers the same. And so a model going from one, you build the model on your machine in the office, and then you need to distribute it. And so we have our TensorFlow serving cloud on premium. That's what I was talking about if you're like a banking or something like that. Now they have TensorFlow Lite, so you can actually run a TensorFlow on an Android or an iOS or Raspberry Pi. Little breakout board there. In fact, they just came out with a new one that has a built-in, it's just a little mini TPU with the camera on it so it can pre-process a video. So you can load your TensorFlow model onto that. Talking about an affordable way to beta test a new product. You have the TensorFlow JS, which is for browser and node server. So you can get that out on the browser for some simple computations that don't require a lot of heavy lifting, but you want to distribute to a lot of endpoints. And now they also have other language bindings. So you can now create your TensorFlow backend, save it, and have it accessed from C, Java, Go, C#, Rust, R, or from whatever package you're working on. So we kind of have an overview of the architecture and what's going on behind the scenes, and in this case, what's going on as far as distributing it. Let's go ahead and take a look at 3 specific pieces of TensorFlow. And those are going to be constants, variables, and sessions. So very basic things you need to know and understand when you're working with the TensorFlow setup. So constants in TensorFlow. In TensorFlow, constants are created using the function constant. In other words, they're going to stay static the whole time, whatever you're working with. The syntax for constant value, dtype 9, shape equals none, name constant, verify shape equals false. That's kind of the syntax you're looking at. And we'll explore this with our hands on a little more in depth. And you can see here we do z equals tf.constant, 5.2, name equals x, dtype is a float. That means that we're never going to change that 5.2. It's going to be a constant value. And then we have our variables in TensorFlow. Variables in TensorFlow are in memory buffers that store tensors. And so we can declare a 2x3 tensor populated by ones. You could also do constants this way, by the way. So you can create an array of ones for your constants. I'm not sure why you do that, but you might need that for some reason. In here we have v equals tf.variables, and then in TensorFlow you have tf.ones, and you have the shape, which is 2, 3, which is then going to create a nice 2 by 3 array that's filled with ones. And then of course you can go in there and they're variables, so you can change them. It's a tensor, so you have full control over that. And then you of course have sessions in TensorFlow. A session in TensorFlow is used to run a computational graph to evaluate the nodes. And remember, when we're talking about graph or graph X, we're talking about all that information then goes through all those arrows and whatever computations they have that take it to the next node. And you can see down here where we have import TensorFlow as TF. If we do x equals a TF.constant of 10, we do y equals a TF constant of 2.0 or 20.0, and then you can do z equals TF.variable, and it's a TF.add x comma y. And then once you have that set up in there, you go ahead and init your TF global variables initializer with TF session as session. You can do a session run init, and then you print the session run y. And so when you run this, you're going to end up with, of course, the 10 plus 20 is 30. And we'll be looking at this a lot more closely as we actually roll up our sleeves and put some code together. So let's go ahead and take a look at that. And for my coding today, I'm going to go ahead and go through Anaconda, and then I'll use specifically the Jupyter Notebook on there. And of course, this code is going to work whatever platform you choose, whether you're in a notebook, the Jupyter Lab, which is just the Jupyter Notebook but with tabs for larger projects. We're going to stick with Jupyter Notebook. PyCharm, whatever it is you're going to use in here. You have your Spider and your Qt console for different programming environments. The thing to note, it's kind of hard to see, but I have my main Pi 3.6. Right now, when I was writing this, TensorFlow works in Python version 3.6. If you have Python version 3.7 or 3.8, you're probably going to get some errors in there. Might be that they've already updated it and I don't know it, and I have an older version. But you want to make sure you're in a Python version 3.6 in your environment. And of course, in Anaconda, I can easily set that environment up. Make sure you go ahead and pip in your TensorFlow, or if you're in Anaconda, you can do Anaconda install TensorFlow to make sure it's in your package. So let's just go ahead and dive in and bring that up. This will open up a nice browser window. I just love the fact I can zoom in and zoom out depending on what I'm working on, making it really easy to adjust a demo for the right size. Go under New, and let's go ahead and create a new Python. And once we're in our new Python window, this is going to leave it untitled. Let's go ahead and import. Import TensorFlow as TF. At this point, we'll go ahead and just run it real quick. No errors. Yay! No errors. I do that whenever I do my imports because I invariably will have opened up a new environment and forgotten to install TensorFlow into that environment. Or something along those lines. So it's always good to double check. And if we're going to double check that, it's also good to know what version we're working with. And we can do that simply by using the version command in TensorFlow, which you should know is probably intuitively the TF dot underscore underscore version underscore underscore. And it always confuses me because sometimes you do tf.version for one thing, you do tf.underscore version underscore for another thing. This is a double underscore in TensorFlow for pulling your version out. And it's good to know what you're working with. We're going to be working in TensorFlow version 2.1.0. And I did tell you we were going to dig a little deeper into our constants, and you can do an array of constants. And we'll just create this nice array, a equals tf.constant. And we're just going to put the array right in there, 4361. We can run this, and now that is what a is equal to. And if we want to just double check that, remember we're in Jupyter Notebook where I can just put the letter A, and it knows that that's going to be print. Otherwise, you'd surround it in print. And you can see it's a TF tensor. It has the shape, the type, and the array on here. It's a 2 by 2 array. And just like we can create a constant, we can go ahead and create a variable. And this is also going to be a 2 by 2 array. And if we go ahead and print the V out, we'll run that. And sure enough, there's our TF variable in here. Then we can also, let's just go back up here and add this in here. I could create another tensor, and we'll make it a constant this time. And we'll go ahead and put that in over here. We'll have B TF constant. And if we go ahead and print out V and B, we go ahead and run that. And this is an interesting thing that happens in here. You'll see right here when I print them both out, what happens is it only prints the last one unless you use print commands. So important to remember that in Jupyter Notebooks. But we can easily fix that by go ahead and print and surround V with brackets. And now we can see with the two different variables we have the 3152, which is a variable, and this is just a flat constant, so it comes up as a TF tensor shape 2 kind of 2. And that's interesting to note that this label is a TF.tensor and this is a TF variable. So that's how it's looking in the back end when you're talking about the difference between a variable and a constant. The other thing I want you to notice is that in variable we capitalize the V, and with the constant we have a lowercase c. Little things like that can lose you when you're programming and you're trying to find out, hey, why doesn't this work? So those are a couple little things to note in here. And just like any other array in math, we can do like a concatenate the different values here. And you can see we can take AB concatenated. You just do a tf.concat values, and there's our AB axes on 1. Hopefully you're familiar with axes and how that works when you're dealing with matrices. And if we go ahead and print this out, you'll see right here we end up with a tensor. So let's put it in as a constant, not as a variable. And you have your array 4378 and 6145. It's concatenated the two together. And again, I want to highlight a couple things on this. Our axes equals 1. This means we're doing the columns. So if you had a longer array, like right now we have an array that is like, has a shape 1, whatever it is, 2, 2. Axes 0 is going to be your first one, and axes 1 is going to be your second one. And it translates as columns and rows. If we had a shape, let me just put the word shape here. So you know what I'm talking about, and it's very clear. And this is, I'll tell you what, I spend a lot of time looking at these shapes and trying to figure out which direction I'm going in and whether to flip it or whatever. So you can get lost in which way your matrix is going and which is column, which is rows. Are you dealing with the third axis or the second axis? Axis 1, 0, 1, 2, that's going to be our columns. And if you can do columns, then we also can do rows, and that is simply just changing the concatenate. We'll just grab this one here and copy it. We'll do the whole thing over. Control copy, Control V, and changes from axis 1 to axis 0. And if we run that, you'll see that now we concatenate by row as opposed to column. And you have 4, 3, 6, 1, 7, 8, 4, 7. So it just brings it right down and turns it into rows versus columns. You can see the difference there, your output. This really, you want to look at the output sometimes just to make sure your eyes are looking at it correctly and it's in the format. I find visually looking at it is almost more important than understanding what's going on, because conceptually your mind just too many dimensions sometimes. The second thing I want you to notice is this says a NumPy array. So TensorFlow is utilizing NumPy as part of their format as far as Python's concerned. And so you can treat this output like a NumPy array because it is just that. It's going to be a NumPy array. Another thing that comes up more than you would think is filling one of these with zeros or ones. And so you can see here we just create a tensor tf.zeros. And we give it a shape. We tell it what kind of data type it is. In this case, we're doing an integer. And then if we print out our tensor, again, we're in Jupyter, so I can just type out tensor. And I run this, you can see I have a nice array of with shape 3, 4 of zeros. One of the things I want to highlight here is integer 32. If I go to the TensorFlow data types, I want you to notice how we have float 16, float 32, float 64, complex. If we scroll down, you'll see the integer down here, 32. The reason for this is that we want to control how many bits are used in the precision. This is for exporting it to another platform. So what would happen is I might run it on this computer where Python does a float to indefinite, however long it wants to. And then we can take it, but we want to actually say, hey, we don't want that high precision. We want to be able to run this on any computer. And so we need to control whether it's a TF float 16. In this case, we did an integer 32. We could also do this as a float. So if I run this as a float 32, that means this has a 32-bit precision. You'll see 0 point whatever. And then to go with zeros, we have ones, if we're going from the opposite side, and so we can easily just create a TensorFlow with ones. And you might ask yourself, why would I want zeros and ones? And your first thought might be to initiate a new tensor. Usually we initiate a lot of this stuff with random numbers because it does a better job solving it. If you start with a uniform set of ones or zeros, you're dealing with a lot of bias. So be very careful about starting a neural network for one of your rows or something like that with ones and zeros. On the other hand, I use this for masking. You can do a lot of work with masking. You can also have, it might be that one tensor row is masked, 0 is false, 1 is true, or whatever you want to do it. And so in that case, you do want to use the zeros and ones. And there are cases where you do want to initialize it with all zeros or all ones, and then swap in different numbers as the tensor learns. So it's another form of control. But in general, you see zeros and ones, you usually are talking about a mask over another array. And just like in NumPy, you can also do reshapes. So if we take our, remember this is shaped 3, 4, maybe we want to swap that to 4, 3. And if we print this out, you will see, let me just go and do that, Control V, let me run that. And you'll see that the order of these is now switched. Instead of 4 across, now we have 3 across and 4 down. And just for fun, let's go back up here where we did the ones. And I'm going to change the ones to tf.randomUniform. And we'll go ahead and just take off, well, we'll go ahead and leave that. We'll go ahead and run this. And you'll see now we have 0.0441. And this way you can actually see how the reshape looks a lot different. 0.041, 0.15, 0.71. And then instead of having this one, it rolls down here to the 0.14. And this is what I was talking about. Sometimes a lot of times you fill these with random numbers. And so this is the random.uniform is one of the ways to do that. Now, I just talked a little bit about this float 32 and all these data types. One of the things that comes up, of course, is recasting your data. So if we have a D-type float 32, we might want to convert these to integers because of the project we're working on. I know one of the projects I've worked on ended up wanting to do a lot of round off so that it would take a dollar amount or a float value and then have to round it off to a dollar amount. So we only wanted 2 decimal points. And in which case you have a lot of different options. You can multiply by 100 and then round it off or whatever you want to do. There's a lot of, or then convert it to an integer was one way to round it off. Kind of a cheap and dirty trick. So we can take this and we can take the same tensor and we'll go ahead and create a as an integer. And so we're going to take this tensor, we're going to tf.cast it, and if we print tensor, and then we're going to go ahead and print our tensor. Let me just do a quick copy and paste. And when I'm actually programming, I usually type out a lot of my stuff just to double check it. In doing a demo, copy and paste works fine, but sometimes be aware that copy and paste can copy the wrong code over. Personal choice, depends on what I'm working on. And you can see here we took a float 32, 4.6, 4.2, and so on, and it just converts it right down to a integer value. Sorry, integer 32 setup. And you remember we talked about a little bit about reshape as far as flipping it, and I just did 4, 3 on the reshape up here, and we talked about axis 0, axis 1. One of the things that is important to be able to do is to take one of these variables. We'll just take this last one, tensor as integer, and I want to go ahead and transpose it. And so I can do, we'll do a equals tf.transpose. And we'll do our tensor integer in there. And then if I print the A out and we run this, you'll see that's the same array, but we've flipped it so that our columns and rows are flipped. This is the same as reshaping. So when you transpose, you're just doing a reshape. What's nice about this is that if you look at the numbers, the columns, when we went up here and we did the reshape, they kind of roll down to the next row. So you're not maintaining the structure of your matrix. So when we do a reshape up here, they're similar, but they're not quite the same. And you can actually go in here and there's settings in the reshape that would allow you to turn it into a transform. So when we come down here, it's all done for you. And so there are so many times you have to transpose your digits that this is important to know that you can just do that. You can flip your rows and columns rather quickly here. And just like NumPy, you can also do your different math functions. We'll look at multiplication. And so we're going to take matrix multiplication of tensors. We'll go ahead and create A as a constant, 5839. And we'll put in a vector V, 4, 2. And we could have done this where they matched, where this was a 2 by 2 array. But instead, we're going to do just a 2 by 1 array. And the code for that is your tf.matmul, so matrix multiplier. And we have A times V, and if we go ahead and run this, let's make sure we print out our AV on there. And if we go ahead and run this, you'll see that we end up with 36 by 30. And if it's been a while since you've seen the matrix math, this is 5 times 4 plus 8 times 2, 3 times 4 plus 9 times 2. And that's where we get the 36 and 30. Now, I know we're covering a lot really quickly as far as the basic functionality. So the matrix, or your matrix multiplier, is a very commonly used back-end tool as far as computing different models or linear regression, stuff like that. One of the things is to note is that just like in NumPy, you have all of your different math. So we have our TF math. And if we go in here, we have functions, we have our cosines, absolute, angle, all of that's in here. So all of these are available for you to use in the TensorFlow model. And if we go back to our example, and let's go ahead and pull, let's do some multiplication. That's always good. We'll stick with our AV, our constant A and our vector V. And we'll go ahead and do some bitwise multiplication, and we'll create an AV, which is A times V. Let's go and print that out. And you can see coming across here, we have the 4, 2 and the 5, 8, 3, 9, and it produces 20, 32, 6, 18. And that's pretty straightforward. If you look at it, you have 4 times 5 is 20, 4 times 8 is 32. That's where those numbers come from. We can also quickly create an identity matrix, which is basically your main values on the diagonal being 1s and 0s across the other side. Let's go ahead and take a look and see what that looks like. And we can do, let's do this. So we're going to get the shape. This is a simple way, very similar to your NumPy. You can do a.shape. And it's going to return a tuple, in this case our rows and columns. And so we can do a quick print. We'll do rows. Oops. And we'll do columns. And if we run this, you can see we have 3 rows, 2 columns. And then if we go ahead and create an identity matrix, the script for that, got a wrong button there. The script for that looks like this, where we have the number of rows equals rows, the number of columns equals columns, and D type is a 32. And then if we go ahead and just print out our identity, you can see we have a nice identity column with our ones going across here. Now, clearly we're not going to go through every math module available. But we do want to start looking at this as a prediction model and seeing how it functions. So we're going to move on to a more of a direct setup where you can actually see the full TensorFlow in use. For that, let's go back and create a new setup. And we'll go in here, new Python 3 module. There we go. Bring this out so it takes up the whole window, because I like to do that. Hopefully you made it through that first part and you have a basic understanding of TensorFlow as far as being a series of NumPy arrays. You got your math equations and different things that go into them. We're going to start building a full setup as far as the NumPy, so you can see how Keras sits on top of it and the different aspects of how it works. The first thing we want to do is we're going to go ahead and do a lot of imports. Date times, warnings, SciPy. SciPy is your math, so the back-end scientific math. Warnings, because whenever we do a lot of this, you have older versions, newer versions, and so sometimes when you get warnings, you want to go ahead and just suppress them. We'll talk about that if it comes up on this particular setup. And of course, date time. Pandas, again, is your data frame. Think rows and columns. We import it as PD. NumPy is your numbers array, which of course TensorFlow is integrated heavily with. Seaborn for our graphics, and the Seaborn as SNS is going to be set on top of our matplot library, which we import as MPL. And then of course we're going to import our matplot library pyplot as PLT. And right off the bat, we're going to set some graphic colors. Patch force edge color equals true. The style, we're going to use the 538 style. You can look this all up. When you get into matplot library into Seaborn, there are so many options in here. It's just kind of nice to make it look pretty when we start up. That way we don't have to think about it later on. And then we're going to take, we have our MPLRC. We're going to put a patch edge color, dim gray line width. Again, this is all part of our graphics here in our setup. We'll go ahead and do an interactive shell. Node interactivity equals last expression. Here we are, PD for pandas. Options display max columns, so we don't want to display more than 50. And then our matplot library is going to be inline. This is a Jupyter notebook thing, the matplot library inline. Then warnings, we're going to filter our warnings, and we're just going to ignore warnings. That way when they come up, we don't have to worry about them. Not really what you want to do when you're working on a major project. You want to make sure you know those warnings and then filter them out and ignore them later on. And if we run this, it's just going to be loading all that into the background. So that's a little back-end kind of stuff. Then what we want to go ahead and do is we want to go ahead and import our specific packages that we're going to be working with, which is under Keras. Now remember, Keras kind of sits on TensorFlow. So when we're importing Keras and the sequential model, we are in effect importing TensorFlow underneath of it. We just brought in the math, probably should have put that up above. And then we have our Keras models. We're going to import sequential. Now, if you remember from our slide, there was 3 different options. Let me just flip back over there so we can have a quick recall on that. And so in Keras, we have sequential, functional, and subclassing. So remember those 3 different setups in here we talked about earlier. And if you remember from here, we have sequential, where it's going one TensorFlow layer at a time. You go kind of think of it as going from left to right or top to bottom or whatever direction it's going in. But it goes in one direction all the time. Where functional can have a very complicated graph of directions. You can have the data split into 2 separate tensors, and then it comes back together into another tensor. All those kinds of things. And then subclassing is really the really complicated one, where now you're adding your own subclasses into the tensor to do external computations right in the middle of like a huge flow of data. But we're going to stick with sequential. It's not a big jump to go from sequential to functional. But we're running a sequential TensorFlow. And that's what this first import is here. We want to bring in our sequential. And then we have our layers. And let's talk a little bit about these layers. This is where Keras and TensorFlow really are happening. This is what makes them so nice to work with, is all these layers are pre-built. So from Keras, we have layers import dense. From Keras, layers import LSTM. When we talk about these layers, Keras has so many built-in layers. You can do your own layers. The dense layer is your standard neural network. By default, it uses ReLU for its activation. And then the LSTM is a long short-term memory layer. Since we're going to be looking probably at sequential data, we want to go ahead and do the LSTM. And if we go into Keras and we look at their layers, this is a Keras website, you can see as we scroll down for the Keras layers that are built in, we can get down here and we can look at, let's see, here we have our layer activation, our base layers. Activation, layer weight, so there's a lot of stuff in here. We had the ReLU, which is the basic activation that was listed up here for layer activations. You can change those. And here we have our core layers and our dense layers. You have an input layer, a dense layer, and then we've added a more customized one with the long-term, short-term memory layer. And of course, you can even do your own custom layers in Keras. There's a whole functionality in there if you're doing your own thing. What's really nice about this is it's all built in. Even the convolutional layers, this is for processing graphics. There's a lot of cool things in here you can do. This is why Keras is so popular. It's open source, and you have all these tools right at your fingertips. So from Keras, we're just going to import a couple layers, the dense layer and the long short-term memory layer. And then, of course, from sklearn, our scikit, we want to go ahead and do our min-max scaler, standard scaler for pre-editing our data, and then metrics just so we can take a look at the errors and compute those. Let me go ahead and run this, and that just loads it up. We're not expecting anything from the output. And our file coming in is going to be airquality.csv. Let's go ahead and take a quick look at that. This is in OpenOffice. It's just a standard, you can do Excel, whatever you're using for your spreadsheet. And you can see here we have a number of columns, a number of rows. It actually goes down to like 8,000. The first thing we want to notice is that the first row is kind of just a random number put in going down. Probably not something we're going to work with. The second row is Bandung. I'm guessing that's a reference for the profile. If we scroll to the bottom, which I'm not going to do because it takes forever to get back up, they're all the same. The same thing with the status. The status is the same. We have a date, so we have a sequential order here. Here is the jam, which I'm going to guess is the timestamp on there. So we have a date and time. We have our O3, CO, NO2 reading, SO2, NO, CO2, VOC, and then some other numbers here, PM1, PM2.5, PM4, PM10. Without actually looking through the data, some of this I can guess is like temperature, humidity. I'm not sure what the PMs are. But we have a whole slew of data here. So we're looking at air quality as far as an area and a region, and what's going on with our date timestamps on there. And so code-wise, we're going to read this into a pandas data frame. So our data frame, DF is a nice abbreviation commonly used for data frames, equals pd.read_csv, and then the path to it just happens to be on my D drive, separated by spaces. And so if we go ahead and run this, we'll print out the head of our data. And again, this looks very similar to what we were just looking at. Being in Jupyter, I can take this and go the other way. Make it real small so you can see all the columns going across, and we can get a full view of it. Or we can bring it back up in size. That's pretty small on there. Overshot. But you can see it's the same data we were just looking at. We're looking at the number, we're looking at the profile, which is the Bandung, the date, we have a timestamp, our O3 count, CO, and so forth on here. And this is just your basic pandas printing out the top 5 rows. We could easily have done 3 rows, 5 rows, 10, whatever you want to put in there. By default, that's 5 for pandas. Now, I talk about this all the time, so I know I've already said it at least once or twice during this video. Most of our work is in pre-formatting data. What are we looking at? How do we bring it together? So we want to go ahead and start with our date time. It's come in 2 columns. We have our date here, and we have our time. And we want to go ahead and combine that. And then we have, this is just a simple script in there that says combine date time. That's our formula we're building. We're going to submit our pandas data frame and the tab name. When we go ahead and do this, That's all of our information that we want to go ahead and create. And then goes for I in range DF shape 0. So we're going to go through the whole setup, and we're going to list tab append DF location I. And here is our date going in there, and then return the numpy array list tab d types date time 64. That's all we're doing. We're just switching this to a date time stamp. And if we go ahead and do df date time equals combine date time, and then I always like to print, we'll do df head just so we can see what that looks like. And so when we come out of this, we now have our setup on here, and of course it's edited on to the far right. Here's our date time. You can see the format's changed. So there's we've added in the date time column, and we've brought the date over, and we've taken this format here, and it's an actual variable with a 000 on here. Well, that doesn't look good. So we need to also include the time part of this, and we want to convert it into hourly data. So let's go ahead and do that. To do that, to finish combining our date time, let's go ahead and create a little script here to combine the time in there. Same thing we just did. We're just creating a numpy array, returning a numpy array, and forcing this into a date time format. And we could actually spend hours just going through these conversions. How do you pull it from the pandas data frame? How do you set it up? So I'm kind of skipping through it a little fast because I want to stay focused on TensorFlow and Keras. Keep in mind, this is like 80% of your coding when you're doing a lot of this stuff is going to be reformatting these things, resetting them back up so that it looks right on here. And, it just takes time to get through all that. But that is usually what the companies are paying you for. That's what the big bucks are for. And we want to go ahead and a couple things going on here is we're going to go ahead and do our date time. We're going to reorganize some of our setup in here, convert into hourly data. Let me just put a pause in there. Now remember, we can select from DF our different columns we're going to be working with, and you're going to see that we actually dropped a couple of the columns. Those ones I showed you earlier, they're just repetitive data. So there's nothing in there that exciting. And then we want to go ahead and we'll create a second data frame here. Let me just get rid of the DF head. And DF2 is we're going to group by date time, and we're looking at the mean value. And then we'll print that out so you can see what we're talking about. We have now reorganized this, so we put in date time 03 CO. So now this is in the same order as it was before. And you'll see the date time now has our 00, same date 1, 2, 3, and so on. So it's grouped the data together so that it's a lot more manageable and in the format we want, and in the right sequential order. And if we go back to, there we go, our air quality, you can see right here we're looking at these columns going across. We really don't need, since we're going to create our own date time column, we can get rid of those. These are the different columns of information we want, and that should reflect right here in the columns we picked coming across. So this is all the same columns on there. That's all we've done is reformatted our data, grouped it together by date, and then you can see the different data coming out set up on there. And then as a data scientist, first thing I want to do is get a description. What am I looking at? And so we can go ahead and do the df2 describe, and this gives us our describe gives us our basic data analytics information we might be looking for, like what is the mean, standard deviation, minimum amount, maximum amount. We have our first quarter, second quarter, and third quarter numbers also in there. So you can get a quick look at a glance describing the data, or descriptive analysis. And even though we have our quantile information in here, we're going to dig a little deeper into that. We're going to calculate the quantile for each variable. We're going to look at a number of things for each variable. And we'll see right here, Q1, we can simply do the quantile 0.25%, which should match our 25% up here. And we're going to be looking at the min, the max, and we're just going to do this. It's basically we're breaking this down for each different variable in there. One of the things that's kind of fun to do, we're going to look at that in just a second. Let me put the next piece of code in here. We got to clean out some of our, we're going to drop a couple things, our last rows and first row, because those have Usually they have a lot of null values, and the first row is just our titles. So that's important. It's important to drop those rows in here. And so this right here, as we look at our different quantiles, again, it's the same. We're still looking at the 25 quantile here. We're going to do a little bit more with this. So now that we've cleared off our first and last rows, we're going to go ahead and go through all of our columns, and this way we can look at each column individually. And so we'll just create a Q1, Q3, min, max, min IQR, max IQR, and calculate the quantile of I of DF2. We're basically doing the math that they did up here, but we're splitting it apart. That's all this is. And this happens a lot because you might want to look at individual. If this was my own project, I would probably spend days and days going through what these different values mean. One of the biggest data science things we can look at that's important is use your common sense. If you're looking at this data and it doesn't make sense, and you go back in there and you're like, wait a minute, what the heck did I just do? At that point, you probably should go back and double check what you have going on. Now, we're looking at this, and you can see right here, here's our attribute for our O3. So we've broken it down. We have our Q1 5.88, Q3 10.37. If we go back up here, here's our 5.8. We've rounded it off. 10.37's in there. So we've basically done the same math, just split it up. We have our minimum and our max IQR, and that's computed, let's see, where is it? Here we go. Q1 minus 1.5 times IQR. And the IQR is your Q3 minus Q1. So that's the difference between our two different quarters. And this is all data science. As far as the hard math, we're really not, we're actually trying to focus on Keras and TensorFlow. You still got to go through all this stuff. I told you 80% of your programming is going through and understanding what the heck happened here. What's going on? What does this data mean? And so when we're looking in that, we're going to go ahead and say, hey, we've computed these numbers, and the reason we've computed these numbers is if you take the minimum value and it's less than your minimum IQR, that means something's going wrong there. And that usually, in this case, is going to show us an outlier. So we want to go ahead and find the minimum value. If it's less than the minimum IQR, it's an outlier. And if the max value is greater than the max IQR, we have an outlier. And that's all this is doing. Low outlier is found, minimum value, high outlier is found. Really important, actually. Outliers are almost everything in data sometimes. Sometimes you do this project just to find the outliers because you want to know crime detection. What are we looking for? We're looking for the outliers. What doesn't fit a normal business deal? And then we'll go ahead and throw in, just threw in a lot of code. Oh my goodness. So we have, if your max is greater than IQR, print outlier is found. What we want to do is we want to start cleaning up these outliers. And so we want to convert, create a convert nan, x max IQR equals max underscore IQR, min IQR equals min IQR. So this is just saying this is the data we're going to send. That's all that is in Python. And if x is greater than the max IQR and x is less than the min IQR, x equals null. We're going to set it to null. Why? Because we want to clear these outliers out of the data. Now, again, if you're doing fraud detection, you would do the opposite. You would be cleaning everything else that's not in that series so that you can look at just the outlier. And then we're going to convert the nan hum. Again, we have x, max IQR is 100%, min IQR is min IQR. If x is greater than max IQR and x is less than min IQR, again, we're going to return a null value. Otherwise, it's going to remain the same value x equals x. And you can see as we go through the code, if I equals our HUM, then we go ahead and do, that's a column specific to humidity. That's your HUM column. Then we're going to go ahead and run a map on there and convert the non-HUM. You can see here this is just cleanup. We found out that humidity probably has some weird values in it. We have our outliers. That's all this is. And so when we go ahead and finish this and we take a look at our outliers and we run this code here, We have a low outlier, 2.04. We have a high outlier, 99.06. Outliers have been interpolated. That means we've given them a new value. Chances are these days when you're looking at something like these sensors coming in, they probably have a failed sensor in there. Something went wrong. That's the kind of thing that you really don't want to do your data analysis on. So that's what we're doing, is we're pulling that out and then converting it over and setting it up method linear. So we interpolate method linear is just going to fill that data in based on a linear regression model of similar data. Same thing with this up here with the DF2I interpolate. That's what we're doing. Again, this is all data prep. We're not actually talking about TensorFlow. We're just trying to get all our data set up correctly so that when we run it, it's not going to cause problems or have a huge bias. So we've dealt with outliers specifically in humidity. And again, this is one of these things where when we start running, we ran through this, you can see down here that we have our outliers found, high-low outliers, we've migrated them in. We also know there's other issues going on with this data. How do we know that? Some of it's just looking at the data, playing with it until you start understanding what's going on. Let's take the temp value, and we're going to go ahead and use a logarithmic function on the temp value. And it's interesting because it's like, how the heck do you even know to use logarithmic on the temp value? That's domain specific. We're talking about being an expert in air care. I'm not an expert in air care. It's not what I go look at. I don't look at air care data. In fact, this is probably the first air care data setup I've looked at. But the experts come in there and they come to you and say, hey, in data science, this is a exponentially variable on here, so we need to go ahead and do transform it and use a logarithmic scale on that. So at that point, that would be coming from your data. Here we go. Data science programmer overview, does a lot of stuff connecting the database and connecting in with the experts. Data analytics, a lot of times you're talking about somebody who is a data analysis, might be all the way usually a PhD level. Data science programming level interfaces. Database manager, that's going to be the person who's your admin working on it. So when we're looking at this, we're looking at something they've sent to me and they said, hey, domain, air care, this is a skew because the data just goes up exponentially and affects everything else. And we'll go ahead and take that data. Let me just go ahead and run this. Just for another quick look at it, we have our, we'll do a distribution DF. We'll create another data frame from the temp values and then from a data set from the log temp. So we can put them side by side. And we'll just go ahead and do a quick histogram. And this is kind of nice. Plot a figure size. Here's our PLT from Matplot library. And then we'll just do a distribution underscore DF. There's our data frames. This is nice because it just integrates the histogram right into pandas. Love pandas. And this is a chart you would send back to your data analyst and say, hey, is this what you wanted? This is how the data is converting on here. As a data scientist, the first thing I note is we've gone from a 10, 20, 30 scale to 2.5, 3.0, 3.5 scale. And the data itself has kind of been adjusted a little bit based on some kind of a skew on there. So let's jump into, we're getting a little closer to actually doing our cross on here. We'll go ahead and split our data up. And this, of course, is any good data scientists. You want to have a training set and a test set. And we'll go ahead and do the train size. We're going to use 0.75% of the data. Make sure it's an integer. You don't want to take a slice as a float value. Give you a nice error. And we'll have our train size is 75%, and the test size is going to be, of course, the train size minus the length of the data set. And then we can simply do train comma test. Here's our data set, which is going to be the train size, the test size. And then if we go ahead and print this, let me just go ahead and run this. We can see how these values split. It's a nice split of 1,298 and then 433 points of value that are going to be for our setup on here. And if you remember, we're specifically looking at the data set. Where did we create that data set from? That was from up here. That was what we called the logarithmic value of the temp. That's where the data set came from. So we're looking at just that column with this train size and the test, with the train and test data set here. And let's go ahead and do convert an array of values into a data set matrix. We're going to create a little setup in here. We create our data set. Our data set's going to come in. We're going to do a look back of 1. So we're going to look back one piece of data going backward. And we have our data X and our data Y for I in range, length of data set, look back -1. This is creating, let me just go ahead and run this. Actually, the best way to do this is to go ahead and create this data and take a look at the shape of it. Let me go ahead and just put that code in here. So we're going to do a look back 1. Here's our train X, our train Y, and it's going to be adding the data on there. And then when we come up here and we take a look at the shape, there we go, and we run this piece of code here, we look at the shape on this and we have a new, slightly different change on here, but we have a shape of X, 1296, 1, shape of Y, train Y, test X, test Y. And so what we're looking at is that the X comes in, and we're only having a single value out. We want to predict what the next one is. That's what this little piece of code is here for. What are we looking for? Well, we want to look back 1. That's the what we're going to train the data with is yesterday's data. Yesterday says, hey, the humidity was at 97%. What should today's humidity be at? If it's 97% yesterday, is it going to go up or is it going to go down today? If 97, does it go up to 100? What's going on there? And so we're looking forward to the next piece of data, which says, hey, tomorrow's is going to, today's humidity is this. This is what tomorrow's humidity is going to be. That's all that is. All that is stacking our data so that our Y is basically X plus 1, or X could be Y minus 1. And then a couple things to note is our X data. We're only dealing with the one column, but you need to have it in a shape that has it by the columns. So you have the two different numbers. And since we're doing just a single point of data, we have, and you'll see with the train Y, we don't need to have the extra shape on here. Now, this is going to run into a problem. And the reason is that we have what they call a time step. And the time step is that long-term, short-term memory layer. So we're going to add another reshape on here. Let me just go down here and put it into the next cell. And so we want to reshape the input array in the form of sample time step features. We're only looking at one feature. And I mean, this is one of those things when you're playing with this, you're like, why am I getting an error in the numpy array? Why is this giving me something weird going on? So what we're going to do is we're going to add one more level on here. Instead of being 1299.1, we want to go one more. And when they put the code together in the back, you can see we kept the same shape, the 1299. We added the one dimension, and then we have our train X shape 1. And this could have, depends again on how far back in the long short-term memory you want to go. That is what that piece of code is for, and that reshape is. And you can see the new shape is now 1299.11 versus the 1299.1. And then the other part of the shape, 432.11. Again, this is our X in, and of course our test X. And then our Y is just a single column because we're just doing one output that we're looking for. So now we've done our 80%. That's all the writing all the code, reformatting our data, bringing it in. Now we want to go ahead and do the fun part, which is we're going to go ahead and create and fit the LSTM neural network. And if we're going to do that, the first thing we need is we're going to need to go ahead and create a model. And we'll do this sequential model. And if you remember, sequential means it just goes in order. That means if we have two layers, the layers go from layer 1 to layer 2, or layer 0 to layer 1. This is different than functional. Functional allows you to split the data and run two completely separate models and then bring them back together. We're doing just sequential on here. And then we decided to do the long short-term memory. And we have our input shape, which it comes in. Again, this is what all this switching was. We could have easily made this 1, 2, 3, or 4 going back as far as the end number on there. We just stuck to going back 1. And it's always a good idea when you get to this point, where the heck is this model coming from? What kind of models do we have available? And let me go ahead and put the next model in there, because we're going to do two models. And the next model is going to go ahead and we're going to do dense. So we have model equals sequential, and then we're going to add the LSTM model, and then we're going to add a dense model. And if you remember from the very top of our code, where we did the imports, oops, there we go, our cross, this is it right here. Here's our importing a dense model, and here's our importing an LSTM. Now, just about every TensorFlow model uses dense. Your dense model is your basic forward propagation, reverse propagation error, where it does reverse propagation to program the model. So any of your neural networks that you've already looked at that looks and says, here's the error, and sends the error backwards, that's what this is. The long short-term memory is a little different. The real question that we want to look at right now is, where do you find these models? What kind of models do you have available? And so for that, let's go to the Keras website, which is the keras.io. If you go under API/layers, and I always have to do a search, just search for Keras API layers. It'll open up and you can see we have your base layers right here, class, trainable, weights, all kinds of stuff like there. Your activation, so a lot of your layers you can switch how it activates. ReLU, which is like your smaller arrays, or if you're doing convolutional neural networks, the convolution usually uses a ReLU. Your sigmoid, all the way up to softmax, softplus, all these different choices as far as how those are set up. And what we want to do is we want to go ahead, and if you scroll down here, you'll see your core layers, and here is your dense layer. So you have an input object, your dense layer, your activation layer, embedding layer. This is your kind of your one setup on there that's most common. Convolutional neural networks, or your convolutional layers, these are like for doing image categorizing, so trying to find objects in a picture, that kind of thing. We have pooling layers, so as you have the layers come together, usually you bring them down into a single layer, although you can still do like global max pooling 3D. And there is just, I mean, this list just goes on and on. There's all kinds of different things hidden in here as far as what you can do. And it changes. You know, you go in here and you just have to do a search for what you're looking for, and figure out what's going to work best for you as far as which project you're working on. Long short-term memory is a big one, because this is when we start talking about text. What if someone says what comes after the cat in the hat, little kid's book there, starts programming it, and so you really want to know not only what's going on, but it's going to be something that has a history. The history behind it tells you what the next one coming up is. Now, once we've built all our different, we built our model, we've added our different layers we went in there, play with it. Remember, if you're in functional, you can actually link these layers together and they branch out and come back together. If you do the sub setup, then you can create your own different model. You can embed a model in there that might be linear regression. You can embed a linear regression model as part of your functional split, and then have that come back together with other things. So we're going to go ahead and compile your model. This brings everything together. We're going to put in what the loss is, which we'll use the mean squared error. And we'll go ahead and use the atom optimizer. Clearly, there's a lot of choices on here depending on what you're doing. And just like any of these different prediction models, if you've been doing any scikit from Python, you'll recognize that we have to then fit the model. So what are we doing in here? We're going to send in our train X, our train Y. We're going to decide how many epochs we're going to run it through. 500 is probably a lot for this. I'm guessing it'd probably be about 200 or 300, probably do just fine. Our batch size. So how many different, when you process it, this is the math behind it. If you're in data analytics, you might try to know what this number is as a data scientist, where I haven't had the PhD level math that says this is why you want to use this particular batch size. You kind of play with this number a little bit. You can dig deeper into the math, see how it affects the results depending on what you're doing. And there's a number of other settings on here. We did verbose 2. I'd have to actually look that up to tell you what verbose means. I think that's actually the default on there if I remember correctly. There's a lot of different settings when you go to fit it. The big ones are your epoch and your batch size. Those are what we're looking for. And so we're going to go ahead and run this. And this is going to take a few minutes to run because it's going through 500 times through all the data. So if you have a huge data set, this is the point where you're kind of wondering, oh my gosh, is this going to finish tomorrow? If I'm running this on a single machine and I have a terabyte